Welcome everybody. My name is Thomas and today we are talking about proof part 2 through 8 of Leibniz's work on the arithmetic quadrature of the circle, parabola and hyperbola. And in proposition 6 the aim is to prove the indivisible method. And the indivisible method which Leibniz lays out here is somewhat different from what was known as indivisible method at the time, because Leibniz sort of combined the method of exhaustion with the indivisible method, and he was doing so by basically trying to show that if you place more and more numbers of points on the semicircular curve and hence make the distance between neighboring ordinates very small, the areas which are created by it and by means of our construction principle of the tangents and their verticals from the intersection points with the conjugate axis, that they converge to one and the same figure, namely what he called the resecting figure. And the terming of this, what is to be proven, is actually very clever, because it sort of states that you can make the difference between the red area being what is named the quadrilinear shape and the green area, which is termed the elementary rectangle. The difference between the two can be made arbitrarily small, depending on how many points you place along the semicircular curves, or in how many sort of sections you divide the semicircular curve. And that is a major difference also to the other methods of the indivisibles, that he is not actually straight looking at the figure which the aim is to quadrate, but he is sort of drawing out another figure which stands in a interesting relationship to the semicircle or the circular figure, and is trying to show that both areas, the quadrilinear shape and the elementary rectangle, converge to the very same area based on the construction principle if you place the ordinates sort of very small distances away from each other, even if you make these ordinate distances infinitely small. And by doing so, or in order to show this, he was creating another rectangle, which he termed the complementary rectangle. We have drawn this out now in blue. This is basically the rectangle where the upper left corner and the lower right corner are basically determined by the intersection points of the ordinates with the resecting figure. Yeah, the resecting figure again is actually partly being produced by the ordinates themselves, namely where these ordinates intersect with the vertical from the tangent intersection points with the conjugate axis. So and hence he said that both these areas are going to converge to the same type of figure, and he said that the difference between the two can be made arbitrarily small, depending on the number of points you place on the semicircular curve. And now let's have a look at the relationship within the complementary rectangle. And there you see that it encapsulates a part of the elementary rectangle and a part of the quadrilinear figure. And both of these areas, they overlap in a certain region, which is this one between D1, F1, P1, E1. And therefore this part sort of cancels itself out when you look at it in terms of the difference between those two areas. Hence we would be able to remove this little section, and we will get these two triangles, the triangle D1, N1, F1, which is the remaining part of the elementary rectangle, and the remaining part of the quadrilinear shape being the triangle of P1, F1 and D4. And you already see that these two triangles are already smaller than the complementary rectangle itself, and hence it is no problem of conceiving that the difference between those two triangles must be also smaller than the area of the complementary rectangle itself. And now the trick is to say that by placing an appropriate number of points on the semicircular curve, and by doing so making the ordinate intervals between these points or between these or its ordinates arbitrarily small, you also make the area of the complementary rectangle arbitrarily small. And because the area of the complementary rectangle is already arbitrarily small, the difference between those two triangles, which really represent the difference also between the entire quadrilinear shape in red and the entire elementary rectangle in green, this difference must also become arbitrarily small, or if you will, even smaller than arbitrarily small. And the terming arbitrarily small is actually very cleverly chosen because it does not really exclude the realm of infinity. So if you place an infinite number of points on the curve, hence making the difference between two consecutive ordinates very small or infinitely small, you also make the complementary rectangle's area infinitely small. And knowing of these differences, or this difference between those two triangles representing the difference between the elementary rectangle and the quadrilinear shape, this difference becomes smaller than infinitely small, or also infinitely small, if you will. And this signifies that because both of these figures converge toward the same figure, being the resecting figure, this actually means that you can use these entities of infinitely slim rectangles, if you will, you can treat them as lines. So not as a line in a original sense, because a line which is of a one-dimensional character, but you still use it as an area. So you have an infinitesimally slim rectangle which you treat as a line. Because that was actually Bonaventura Cavalieri's approach of defining the area by a sum of lines, which is actually not true, because when you think about it, when you sum up lines which have one dimension being 0, then you don't get an area, because summing up a lot of zeros doesn't get you an area, or doesn't open up another dimension. But rather you have to deal with the infinitesimals, and it was originating from John Wallis, who was the first one to, instead of dividing an area of interest into a bunch of lines, he was dividing it into what he called infinitesimals, or infinitely small parallelograms. and he was computing the area of interest from the sum of these parallelograms. And Leibniz took it a step further by basically sort of combining the method of exhaustion, which you can relate to as in terms of placing an infinite number of points on the semicircular curve, and therefore dissecting this semicircular curve into an infinite number of sectors and summing them up later. And in the process of summing up, instead of using lines as Cavalieri did, Leibniz uses these infinitesimally slim rectangles, which in the terminology at least he treats as lines. So, but he's always being very careful of stating that you can term them lines, or you can name them, these infinitesimally slim rectangles, you can name them lines, while they're actually not lines. They are of the same dimension as the area itself. They have one dimension in one axis, and even if infinitely small, they still have a dimension in the other axis. And it's just the case that it is in the direction of one axis, the area is infinitely small, or the component of this axis becomes infinitely small as you do so. And that's laying the very basis of his further development of the infinitesimal calculus, and it also lays the basis of his great achievement of giving the scientists and the engineers at hand an operation, a mathematically based operation, where you can treat these infinitesimals very easily. And there is actually the great achievement, and the basis for this achievement is being displayed here as proof of the indivisibles. Yeah, he was combining the method of exhaustion, the indivisible method of Cavalieri, and how it was developed further by John Wallis into something treatable in terms of getting an entity of an area, an infinitesimally slim rectangle, if you will, which you can treat as line. And like Cavalieri, he is then summing up lines, but lines which are in reality infinitesimally slim rectangles. So, and hence this is true for a single point pair and a single pair of ordinates, that the difference between those two areas, the red one being the quadrilinear area and the green one being the elementary rectangle, the difference between them can be made arbitrarily small, and it should be smaller than the area of the complementary rectangle in blue. He said that this must also be the case if you place more than one of these rectangles on the curve. So you place like 4 points on the curve. That gives you 3 ordinate pairs, all of which will create an elementary rectangle, a quadrilinear area, and a complementary rectangle. And it must be the case, because the relationship applies to all of them, that the area or the sum of the areas of the complementary rectangles will be larger always than the difference between, or the sum of the difference between the quadrilinear shapes and the rectangular, the elementary rectangles. And so the sum of the blue complementary rectangles will always be larger than the sum of the differences between the quadrilinear shapes and the elementary rectangles. And that was the basic conception, that what applies to one section or one ordinate pair, it must be also true for the sum of those. And we're trying to demonstrate this by sort of dynamically placing an increasing number of points on the circular curve, and therefore producing ever smaller ordinate intervals, which in turn produce ever smaller complementary rectangles by applying our known construction principle of the tangents and secants of each point. And additionally, we placed on the very last complementary rectangle sort of a zoom magnifier, and the magnification factor of this sort of virtual lens or zoom objective, if you will, is increasing as you decrease the size of the ordinate interval. And this is just to show, in the very same principle as Nicholas of Cusa actually did when he was looking at Archimedes' work of the method of exhaustion in the quadrature of the circle. And then Cusa actually stated that you cannot definitely quadrate the circle by the method of exhaustion, because if you inscribe into a circle polygons with an ever larger number of corners, you may get very close to what the circle represents, but at the same time you actually make this sort of polygon shape increasingly different from the circles, because you increase the number of corners. And since the circle has no corner, and you compare it to an object which has more and more corners, instead of making this object more equal or more closer to the originating circle figure, you make it actually conceptually more different, because you introduce more corners. And this can only become round by looking at the infinitesimals, which got coined and developed by John Wallis, and then successively also by Gottfried Wilhelm Leibniz. And the point is, as I increase the number of points on the curve, as I am just doing now, you see that at some stage it must not even be a lot of points. I mean, 200 points around is not really a lot, but it's also enough to show the principle that these little complementary rectangles become already inconceivably small if you look at those being placed around the resecting figure. And but what is remaining is the principle, the relationship between the areas involved, namely being the elementary rectangle, being the quadrilinear shape, and being the complementary rectangle. So the relationship stays intact, that the difference between the red and the green area is always going to be smaller than the area of the complementary rectangle. And now we are at around 300 points, 400 points, and these rectangles appear to us, as conceived by our senses, as points, while the zoom magnifier is clearly showing us that we are still dealing with rectangles and the complementary rectangles and what it encapsulates in terms of the elementary rectangle and the quadrilinear shape. And this way you could actually proceed forever. You could go up as long as you like, and you could go up into infinity you would still deal with this relationship. You can't eliminate this relationship. While you can sort of eliminate or make the quantities vanish, the principle will remain. And that is also valid for the realm of infinity. And that's the trick for the whole calculus, and that's why it works. Because the conception that the relationship between infinitesimally small areas which have a certain relationship in the finite, that the same relationship is actually valid in the infinite. And hence you can treat these areas or these ordinate intervals as lines in the infinitely. If you have this distance of the ordinate interval, or the height of the ordinate interval being infinitely small. But because not this distance not being zero, but just infinitely small, and that bears a great difference because it maintains this dimension. It maintains the dimension in which these rectangles are actually slim or infinitely small, and that makes the difference of being capable of actually summing up these infinitesimally small areas such that you don't sum up a bunch of lines, which at the end would still give you a line, because a line has a dimension of 0 in the line width, if you will. So that is the major difference. And another aspect of this viewpoint actually becomes visible as we shall draw out a little comparison. So we made the ordinate intervals to some degree conceivable now, and now we draw out the verticals from each side line of each complementary rectangle. And what you could do now is you basically could take each and every one of these complementary rectangles and drop it to the very last ordinate interval. And because we made these intervals equidistant, they will all fit into the last ordinate interval. And the sum of those complementary rectangles would basically constitute this rectangle down here, being L1, D4 and psi. And that is basically the same area as the sum of all areas of the all complementary rectangles involved. So, and by doing this, you can actually very clearly show that the principle stays intact within these complementary rectangles. The relationships based on our little tetragonism construction principle, the relationships between the complementary rectangle, the elementary rectangle, and the quadrilinear shape. Because if we go on now placing an increasing number of points on this curve, we increase the number of complementary rectangles, and we make these complementary rectangles very small, and now it would be very tempting to think that these rectangles sort of vanish into points when it comes to the realm of infinity. And this little example here is actually clearly showing that this is not the case. So if I go above the 400 points we were introducing right now, you could go on forever until infinity, and you visually would conceive the sum of these complementary rectangles along the resecting figure as this blue line here. And it is the same, actually in the same area as the line down here. So that is clearly showing that the principle is staying intact, that you're still looking at a succession of rectangles, because the line of the resecting figure at this part, the blue line, is clearly, conceivably longer than the line down here at the bottom at the very last ordinate interval. Because we're dropping all these complementary rectangles down to the very last interval. And it shows that even if I made this number of points and the number of ordinate intervals infinitely large, you would still basically change nothing about the length of this line, or rather this succession of elementary or complementary rectangles, and it would down here always be smaller than the visually conceived line of the succession of those complementary rectangles being placed along the resecting figure. And this is because the relationship complementary, or the principal complementary rectangle, remains, as you can clearly see in our little dynamic magnifier here, which is pointing to the very last complementary rectangle at the bottom ordinate interval. And this is actually this little complementary rectangle just being magnified, in our case, like 44 times. And this line is basically longer than this line because it refers to a succession of the diagonals of the complementary rectangle, while this line refers to a succession of the complementary rectangle's width, and the width is always smaller than the diagonal of the same rectangle, and that's why this line is shorter than this line, although it is composed of the same number of the same complementary rectangles. And this is actually another demonstration or proof that principles or geometric relations stay valid, even though if you move into the realm of infinity. And hence, this is the case. It has been shown and demonstrated this way that you can treat these infinitesimally small ordinate intervals as lines, and you actually could use the areas 1 being the elementary rectangles and treat them as lines, and hence you can sort of sum these quasi-lines, or being actually infinitesimally small areas, you can sum them up just like they used to be at the time with the Cavalieri method. But this time you do it with actual areas, infinitely small areas. And this is what he was to show, and therefore he was laying the basis for the whole continued development of the infinitesimal calculus. And at the last part of this little demonstration, I would like to read out now what Leibniz wrote on the closure of this proposition, and also a little scholium which he created, which is going to tell you something about the nature of his thinking and how he was treating certain aspects of his work with regards to other people's work, especially Newton. So I'm going to read out the closure. And he wrote, this proposition needed a long stretching proof because our indivisible method is significantly different from the usual others, at least in this case. But if yet in one of these other cases being different from ours, some curve n1, n2, n3 would have been gone through these points n1, n2, and 3, just as it is the case with usual indivisible methods, where curved figures are only divided into parallelograms. And he clearly refers to the method of John Wallis, who actually divided areas into infinitely small parallelograms. The proof would have been a lot easier. For the difference between the stair-shaped area n1, b1, b3, p2, n2, p1, n1, and the mixed line n1, b1, b3, and n3, n2, n1 would consist of these small three-lined areas n1, p1, n2, n1, and n2, p2, n3, n2, which are smaller than the rectangles n1, p1, n2, n2, p2, p3, which circumscribe them, which we shall call complementary. Thus also the mentioned difference will be smaller than the sum of those complementary rectangles. But the sum of those complementary rectangles will never be larger than the rectangles which is made by the sum of their baselines p1, n1, p2, n2, which is never larger than the line b3, n3, multiplied by the height of 1, if the heights of all of them are equal, as it is usually assumed with concurrent indivisible methods, or if it is unequal to the others with the largest. If thus the last one is said to be the largest, or at least equal to the others, the aforementioned difference will never be larger than the rectangle b2, b3, n3. Since its height can be made arbitrarily small, so can also the difference between the four-lined or the quadrilinear area 2 and the stair-shaped area 1 be made smaller than any given area. Now the sum of the elementary rectangles n1, b1, b2, p1, and n2, b2, b3, p2, and the others, etc., meaning those which form the stair-shaped area n1, b1, b3, p2, n2, p1, n1, is equal to the sum of the baselines, namely the ordinates b1, n1, b2, n2, b3, n3, multiplied by the common height if the interval b1, b2, or b2, b3 is set as always equal. Thus, we can also measure the stair-shaped area by the sum of the attached ordinates multiplied with the always equal interval between two neighboring ordinates. But the stair-shaped area can be continued as far as that the difference between itself and the mixed line, or what's referred to as the quadrilinear shape, will be smaller than any given area, as shown previously. If thus something can be proven in this form about the summation of lines and the content of a stair-shaped area, such that it is valid, however far the stair-shaped area will be continued, or that it is most valid if the intervals of the attached ordinates are sufficiently small, then it will be true for the quadrilinear shape as well, or the error, if one can be induced, will be smaller than any assignable error. Hence, it will be permitted to use the indivisible method, which progresses by stair-shaped areas or by sums of ordinates, as a strictly proven one. And this is a clear statement that he now, due to this proof of the indivisible method, is regarding these infinitely small areas of the elementary rectangles in green. He will use them as sums of ordinates, or sums of lines in his later terminology, while in reality they are still infinitely slim rectangles, if you will. Okay, and now let's move on to the scholium, which is also very interesting. He wrote, I, so Leibniz, rather would have gone over this, I would rather have overgone this proposition, because nothing is further from my mind than the over-precise pedantisms of some authors who are more interested in show than in results, for they also equally consume time for some ceremonies and have more work than understanding, and cover the origin of the discoveries, which mostly seems more important to me than the discovery itself, in dark clouded night. So my guess is that he was referring to guys like Newton here in this case. Since I am not denying that in the interest of geometry one possesses strictly proven methods themselves and principles of discoveries, as well as certain specifically important propositions, I had been of the opinion that the old-fashioned ways should be accounted for in some way. And this represents the end of proposition 6, and in which we were showing that the indivisible method was actually strictly proven and now being applicable for the continued development of the infinitesimal calculus. So I hope you enjoyed the trip a little, and I'm hopefully going to see you again in the next movie, which is going to be dealing with proposition 7. Alright, thank you for watching, and bye bye.